Good evening. Today is the week 9 of the live interactive session for the NPTEL course, An Introduction to Climate Dynamics, Variability and Monitoring. Uh, so last class, I think we stopped around here. In this question, we stopped, which was about the factors that do not affect the absorption and emission characteristics of the atmosphere. So, and there are four options from which we have to find the factor that actually do not affect the absorption and emission characteristics of the atmosphere. So we know that the frequency of electromagnetic waves do affect the absorption and emission characteristics of the atmosphere. That is, there is a particular wavelength, there is a particular range of wavelength which is actually sensitive to the atmospheric gases. As we know, like the incoming solar radiation is almost transparent to the as it passes through the atmosphere is almost transparent to the incoming solar radiation, whereas it absorbs the outgoing long wave radiation. So we know that based on the frequency or wavelength of the radiation, the emission and absorption characteristics of the atmosphere changes. So from here, it is among the options, it is clear that the frequency of electromagnetic waves do affect the absorption and emission characteristics of the atmosphere. Then the next one, so this is not the answer. And then we have Earth's temperature. So we know that the energy that is being emitted by a black body, we consider Sun and Earth as black body when we are solving problems. So the emission characteristics of a body or Earth or Sun actually is a factor is determined by the by its surface temperature. So yes, the Earth's surface temperature do affect the emission characteristics of the or this surface. The temperature of the Earth actually determines the absorption and emission characteristics of the that. So that is also not an option. Then we have the amount of N2 in the atmosphere and amount of N2O in the atmosphere. We know that N2 is the most abundant gas in the atmosphere, which almost occupies 78% of the total atmospheric composition. Then we have N2O, which is also seen in the atmosphere in very trace amounts. So, what is the difference between these two? Which one is actually sensitive to the which one does actually determine the absorption and emission characteristics of the atmosphere? So, different molecules. So, we know that N2 is a homoatomic molecule which has two nitrogen atoms held together by a bond. And N2O is a heteroatomic molecule which has two nitrogen atoms and one oxygen atom, which is combined together to form the molecule. So there are different gas molecules in the atmosphere, both homoatomic and heteroatomic. Homoatomic in the sense which has same atoms, which is combining to form a molecule. And then there are heteroatomic molecules which has different atoms. So we have both homoatomic as well as heteroatomic molecules. And the molecular structure of these molecules can be linear like this N2 that is connected by, so this is O2. So like O2, it can be linear. It can be planar or it can be three-dimensional. Planar in the sense like this H2O, oxygen and two hydrogen atoms. Or it can be three-dimensional like CH4. C, then we have H, 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 and H. So there can be different structure for these molecules as well. And the molecules can be homoatomic or heteroatomic. It can be either the structure can be linear, planar, or three-dimensional. Then the molecules can also be non-polar and polar. So what does it mean by polar and non-polar? So non-polar in the sense they doesn't have uh, the charges are basically asymmetric. No asymmetry exists in their charges, and it doesn't have a dipole moment. Whereas there are some molecules which have a dipole moment, which means they have asymmetric positive and negative charged ends. So generally, this is seen in heteroatomic molecules, which will have mismatch of the number of protons and electrons, like whatever, like as we can see here, we have N2O, then we have H2O, then ozone CH4, sorry, ozone H2O, N2O, CO2, etc. So there are certain molecules which have a charge asymmetry in them. So these molecules, some heteroatom molecules will have an asymmetry, and there are some which doesn't have also. Based on their charge distribution, it may have a charge asymmetry or symmetry. So some heteroatomic molecules like the H2O, ozone, and N2O has a permanent dipole moment. So in the atmosphere, these molecules are in gas phase, and so these molecules generally undergo, they can move or they rotate, they are generally moving or they rotate about the same axis or they vibrate like mass on springs. So if a molecule has a dipole moment, so there are both molecules which has a permanent dipole moment and there are some molecules which doesn't have a permanent dipole moment. So if a molecule has a dipole moment, then its rotation causes fluctuation in electric and magnetic field that can resonate with the frequency of electromagnetic radiation. So the molecules that has a permanent dipole moment, when it moves linearly or when it vibrates like a mass on a spring or when it rotates on its own axis, then they may have a it will create a fluctuation in the electric and magnetic field, and they resonate with certain frequency of electromagnetic radiation. They will have a particular frequency of vibration. So when this frequency of vibration matches with the frequency of the electromagnetic radiation that is interacting with the molecule, then this absorption occurs. So molecules with permanent dipole moment like water vapor and N2O absorbs the electromagnetic radiation over certain frequency range. So based on the frequency of the vibration of the molecule and the frequency of the electromagnetic radiation that is actually interacting with the molecule, when they resonate with each other, absorption takes place, and these molecules which is having a permanent dipole moment show generally this characteristics. So here the other two options that we have is N2O in the atmosphere, which is a molecule that has a permanent dipole moment. So here I have listed out some molecules which are both homoatomic and heteroatomic, and you can see the homoatomic molecules like N2O2 doesn't have a permanent dipole moment, whereas heteroatomic molecules like CO, yeah, so heteroatomic molecules like CO, N2O, water, ozone, etc., are having a permanent dipole moment. So, when the molecules which are having a permanent dipole moment interact with the electromagnetic radiation, the absorption takes place. So, here in this question, the question was like which of these factors do not affect the absorption and emission characteristics of the atmosphere? So, homoatomic molecules such as N2O2 and heteroatomic molecules which doesn't have a permanent dipole moment like CO2, CH4, etc., doesn't interact with the electromagnetic radiation that is passing through the atmosphere. So the N2O, which is a heteroatomic molecule and which has a permanent dipole moment, do affect the absorption and emission characteristics of the atmosphere, whereas the amount of N2, which is a homoatomic molecule with the permanent dipole moment, homoatomic molecule with a permanent dipole moment does not affect the absorption and emission characteristics of the atmosphere. So, amount of N2 in the atmosphere is the correct answer. Now, the next question, which of the following absorbs most radiation between 15 to 100 micrometer range of radiation? So, as we were discussing, different molecules have a different frequency of vibration, and when the frequency of vibration of the molecule um, matches with the frequency of the electromagnetic radiation that is interacting with the molecule, the absorption takes place. So each molecule will have its own characteristic frequency of vibration. So generally, isolated molecules um, need photons or electromagnetic radiation of the exact frequency um, of vibration for absorption to occur. So it will have a single frequency value. So here I have given the vibrational modes of different molecules like CO, CO2, N2O, H2O, O3, NO, NO, etc. So as we can see, they have different vibrational modes or like different frequency of vibration. So isolated molecules generally need exact frequency. So the electromagnetic radiation should be of this exact frequency for the absorption to occur for this particular type of molecule. But in the atmosphere, since we have a mixture of various gaseous molecules, they collide with each other. So these um, collisional energy actually broadens the frequency range on which the absorption takes place. So the radiative activation of vibrational mode occur at a broader range of frequencies instead of a single frequency like this. So we will have a different frequency. So we have a broader range of frequency rather than single vibrational frequencies. So this shows the frequency range upon which the absorption takes place for different types of molecule. So this is for carbon monoxide where the absorption generally. So this the y-axis shows the absorption where it is happening to the maximum. So the inverted peak is actually showing more absorption. So as you can see in case of CO, the maximum absorption is taking place around 4 micrometer. In case of CH4, it's just between 3 and 4, and then the second vibrational mode is between 7 to 8 micrometer. And we have for N2O, it is between 4 to 5 and between 8 to 9. And then for ozone, it is around 10 micrometer. And for CO2, we have at 3 micrometer and then at 4 micrometer. Then water vapor is between 5 to 8 micrometer. So we have different frequency ranges. So what was the question? The question was which of the following absorbs most radiation between 15 to 100 micrometer range of radiation? Oxygen, nitrogen, carbon dioxide, methane, water vapor, and nitrous oxide are the options. 15 to 100 micrometer. Sorry, 5 to 100 micrometer. 5 to 100 micrometer occurs in case of water vapor. As we can see, 100% of absorption is actually occurring between 5 to 8 or like from 5 it actually starts. So the answer is water vapor. From the figure, we can see that in case of water vapor, the radiation range is 5 to. So this is the answer. Water vapor, as we can see from the figure. In case of water vapor, the maximum absorption is taking place between 5 to 100 micrometers, from 5 to that range actually. Okay, so yeah, so that is the answer. Water vapor is the answer. Now the next question. The normally directed spectral radiation density at the top of the atmosphere at a certain frequency of radiation is 100 watt per meter square hertz. The optical depth of the atmosphere at the ground level for this frequency was found to be 2. What is the spectral radiation density radiation intensity value received at the ground level for this frequency value? So this is basically how the solar radiation is being transmitted through the atmosphere. We know that as the solar radiation passes through the atmosphere, a lot of energy, lot of the intensity of radiation basically reduces as it reaches the surface of the Earth, as it interacts with the atmosphere, and as it is passing through a particular distance. So as the distance between the top of the atmosphere and the surface is more, there will be more loss in radiation. So this basically, so before solving this equation, we will just derive the equation for the transmission of solar radiation through the atmosphere. Transmission of solar radiation through the atmosphere. So we are ignoring the scattering and reflection of clouds and aerosols. Solar radiation is either getting absorbed or transmitted. We are considering only absorption and or transmission occurs. We are neglecting the scattering and reflection that is happening in the atmosphere for simplicity. So in the question, it is said that normally directed spectral radiation intensity. So suppose this is the surface and this is the atmosphere. So there is some radiation that is coming like this. Then density of the radiation that is coming, that is I nu infinity, is given as 100 watt per meter square hertz. And the optical depth of the atmosphere at the ground level for this frequency is found to be 2. So there is the optical depth is basically the characteristics of the medium through which it is passing through. So it basically gives you how much, it is a measure of how much energy will be lost as it is passing through the atmosphere. So the optical depth is having a value of 2. We need to find what is the frequency of the radiation or the intensity of the radiation that is reaching the surface. So I nu S is equal to question mark. So this is what we need to find out. I nu S is what we have to find out. So let's consider this is the surface of the earth and we have atmosphere over here. This is the normal to the surface. So suppose this is sun. The solar radiation, there is some incoming solar radiation, which is, so it won't always be directly overhead or it may fall on a particular angle to the surface. So let this be theta. And this is the distance of the depth of the atmosphere from the surface to a particular height z. We are considering a small element in the atmosphere. So let this distance be dz. And this is the perpendicular length. And along the solar radiation, the length is given by s. So this is theta and let this be ds. Okay. So the spectral solar intensity spectral solar intensity at the top of the atmosphere is given by I nu infinity and the spectral solar intensity incident on the earth is given by I nu s. Now the atmospheric thickness is z. Atmospheric thickness is z and thickness in the direction parallel to the sun is s, parallel to the solar radiation. Like this distance is s and the perpendicular distance is z. No. S and Z are oppositely directed. So solar radiation as it is incoming, we are measuring it from, it is basically pointing downward like this. And whereas Z, we are measuring from the ground to the top of the atmosphere. So it is basically pointing upward. It is oppositely directed. And at Z is equal to 0. Z is equal to 0 is at the sea level. And S is equal to 0 is at the top of the atmosphere, where Z is equal to infinity. So this is a basic idea. So if the sun, as I said, the solar radiation is not falling normal to the surface. If the sun makes an angle theta with the ground normal, then dz is equal to dz is equal to minus ds cos theta. So this is from this right angle triangle. This is ds and this is dz is the right angle. So since it is directed in the opposite direction, we have that minus sign. Cos theta is basically dz by ds, and dz is equal to minus ds cos theta. Now, according to the Lambert-Boger-Weir law of extinction, according to the Lambert-Boger-Weir law of extinction, the absorption by a layer of depth dz, which is along the path of the radiation beam, the absorption by a layer of depth ds, which is basically along the path of the radiation beam, is proportional to the spectral intensity I nu infinity, which is incident on that layer, times the mass density of the absorber along the path of the radiation. Mass density, so let it be rho I, which is basically a characteristic of the um, medium through which the radiation is passing. So Lambert-Boger-Weir law basically states that the absorption by a layer of depth ds, which is along the path of the radiation beam, is proportional to the intensity of the radiation that is incident on that particular layer times the mass density of the absorber along the path of the radiation, which is rho I. Mass density is given by rho I. And if we introduce a proportionality constant, it will be ds is equal to k nu absorption. K nu absorption I into I nu infinity rho I. So this is basically what the equation states, and the proportionality constant K nu absorption I is having a unit of meter square per kg, and it is basically depends on the frequency of radiation, frequency of the incident radiation. Then it is dependent on the identity. What is the absorbing species that we are talking about? Here we are considering the atmosphere, the absorbing species, and it is also dependent on the temperature and pressure of the medium, T and P of the medium. So according to the Lambert-Boger-Weir law of extinction, the absorption by a layer of depth ds is basically proportional to is basically not ds is proportional to absorption over that layer ds. Absorption would be dA. Absorption along the path ds is proportional to the intensity of the radiation that is incident on that layer. Um, incident on that layer into the mass density of the medium. And if we introduce a proportionality constant k nu, it's the absorption I, which is having a unit of meter square per kg. It is basically dependent on the frequency, the absorbing species, and the temperature and pressure of the medium. The absorption along the path ds is given by. So in this case, atmosphere with a differential thickness dz, spectral intensity at altitude Z. So let's consider the change in intensity dI nu as it passes through the an atmosphere of thickness dz is given by dI nu is equal to k nu absorption I into rho I, which basically gives you the absorption along the path ds into the intensity of the solar radiation into ds, or you can write minus k nu I absorption rho I nu of z is equal to dz divided by cos theta, because ds is basically dz by cos theta. Now we can introduce another. So rho I is the partial density of the absorbing species. So now if we introduce another term known as the optical depth, change in d tau nu is equal to minus k nu absorption I into rho I into dz, get di nu is equal to minus d tau nu into I nu. It's I nu infinity basically, which is the incoming solar radiation. Now if we di nu by I nu is equal to minus d tau nu dz by cos theta. Now we integrate this, the radiation integrating from top of the atmosphere to Z. Integrating from top of the atmosphere to Z. This will be log I nu. It will become log I nu from Z to infinity minus tau nu Z by cos theta. Or you can write I nu of infinity by I nu of Z is equal to exponential of minus tau p by cos theta, where tau nu of Z is equal to minus integral infinity to z k nu I absorption rho I dz. Now from this, so now we know what is the relation between the intensity of incident radiation at the top of the atmosphere and that reaching the surface and the optical depth. So in the question, what all things were given? In the question, I nu infinity is given as 100 watt per meter square. So this is the equation that we need basically. Yeah. So I nu infinity is given as I nu infinity is basically given as 100 watt per meter square hertz, and the optical depth tau is given as 2. Now from this, it is given that the radiation is normally incident on the surface, which means theta is equal to 90 degree. So we can write I nu of Z is equal to, okay, I think it's the other way around. I nu of Z is equal to exponential of minus tau nu into I nu infinity, which will become exponential of minus 2 into 100, which will be a raised to minus 2 is around 0.1353 into 100 is 13.53. 13.53 watt per meter square hertz. This is the answer. And we have different options in the question. Okay, we have 100, 76, 36, and 14 watt per meter square hertz. We got the answer to be 13.53, which is close to 14 watt per meter square hertz. So this is the answer. So we know what is the intensity of the solar radiation that is incident on the top of the atmosphere and the optical depth of the atmosphere. We can calculate the intensity of the radiation that is reaching the ground level. Now, the question is which law states that the absorption by a layer of the atmosphere is proportional to the spectral intensity of the radiation times the mass density of the absorber along the path of the radiation. So we just discussed which law is this while deriving, which is basically Lampert-Beer-Boger law, which basically gives the amount of radiation that is being absorbed as it is passing through an atmosphere. Basically gives you dA, or the amount of radiation that is being absorbed is given by A nu absorption of I into rho I into ds. A nu I absorption rho I ds into I nu, which is the intensity of the incident radiation. So this is what Lampert Boger Bialo states. Proportional to the spectral intensity of the incident radiation, which is I nu of z, times the mass density, which is rho I, along the path of the radiation, which is ds. It basically shows you rho I nu of z into ds is what is dA. Now, if we introduce a proportionality constant, it is dI nu is equal to K nu absorption I, rho I nu of z into ds. So this is Lambert-Boger-Beer law. Now, state true or false. The Earth's emission spectrum peaks around 15 micrometer. Is this true or false? So we know how to find the maximum amount, the wavelength of the maximum amount of radiation that is being emitted by a black body, which is basically given by Wien's displacement law. According to Wien's displacement law, lambda max into T is equal to a constant. If we know the temperature of the black body that we are considering, in order to find the maximum, the wavelength at which maximum emission is occurring is given by Wien's displacement law. So in case of Earth, we know the global mean temperature is 15 degrees Celsius, which is basically 15 plus 273, which is 288 Kelvin. And the constant C is given as 2898 micrometer Kelvin. Yeah. So lambda max is equal to C by T, which is 2898 into 10 raised to minus 6 divided by 288, which will be 2898 divided by 288 is around 10.06 micrometer. So the question was the Earth spectrum peaks around 15 micrometers. So yeah, it peaks around. We are getting a value of 10, which means it peaks around 15 micrometers. So this is true. So we look at the wavelengths, how this is distributed. The energy is distributed along different wavelengths in case of sun and in case of earth. So the first one is basically in case of sun, we can see the emission spectrum peaking around 500 nanometer or zero point 0.5 micrometer. Yeah, 500 nanometer or zero point 0.5 micrometer in case of sun, it is peaking in the visible range. Whereas in case of earth, which is having a temperature of around 255 Kelvin, it is peaking around, so 15 degrees Celsius is approximate temperature. So 250, if we are considering that the earth is having a temperature of around 255 Kelvin, then we will get that the emission peaks at a wavelength of around 15 micrometer. So this is this is basically in the infrared region of the spectrum. So in case of sun, the radiation peaks in the visible range, whereas in case of earth, it peaks in the infrared range of the spectrum. Now, the earth cannot be considered a black body in the UV range as it has a non-zero albedo value. So what does it mean by a black body? What is a black body? So an idealized object that absorbs all radiation incident on its surface is called a black body. So since the black body reflects no radiation, all radiation coming from the surface of the black body is thermal emission dependent on the surface temperature alone. And we are also considering that no reflection happens from the surface of the black body in that particular range. So generally, in case of Earth is considered to be a black body in the infrared range of the spectrum, where it primarily emits thermal radiation to space. And whereas Sun, with a surface temperature of around 6000 Kelvin, is considered to be a black body, is also considered, but in case of Earth, we are considering it to be a black body in the infrared emission range. Since in the UV range, it is having a non-zero albedo value, or it basically reflects all the radiation that is coming in the UV range of the spectrum. Earth cannot be considered a black body in that UV range because when we are considering a black body, we assume that it absorbs all radiation that is incident on its surface and no reflection happens from the surface. And whatever the emission that is taking place from the surface of the body is a characteristic of its surface temperature alone. We generally doesn't consider the albedo when considering a black body. We consider that the albedo is zero. So since Earth reflects back the radiation in the UV range of the spectrum, this statement is basically true, which is basically telling the Earth cannot be considered a black body in the UV range as it has non-zero albedo value. Thus, true. Now, which law states that the fraction of radiation absorbed by a gas will be equal to the fraction of the total blackbody radiation emitted by the same gas. The fraction of radiation absorbed by a gas will be equal to the fraction of the total blackbody radiation emitted by the gas. The absorptivity and emissivity will be same. So in a black body, we basically consider that the emissivity, which is given by E, and the absorptivity, let it be alpha, is equal. So the amount of radiation that is being absorbed by um, the amount of radiation that is being absorbed by a gas um, will be emitted by the gas as well. So this is basically given by the Kirchhoff's law. Just give me a second. Let me just. Yeah. So the Kirchhoff's law basically states that the absorptivity will be equal to the emissivity. So the answer is Kirchhoff's law, which law states that the fraction of radiation absorbed by a gas will be equal to the fraction of the total blackbody radiation emitted by the same gas. So the statement basically goes like this. Kirchhoff's law state that for any material for any material at a given temperature and wavelength for any material at a given temperature and wavelength, its emissivity is equal to its absorptivity. the substances that are good absorbers of thermal radiation are also good emitters. So, yeah. So the statement basically tells the Kirchhoff's law. E is equal to where E is emissivity and alpha is absorptivity. This is what Kirchhoff's law states. Now the next question, calculate the energy of a photon of electromagnetic wave with a frequency of 5 into 10 raised to 14 hertz, where Planck's constant is having a value of 6.626 into 10 raised to minus 34 joule second. Select the nearest correct answer. So we know that the electromagnetic radiation is being transmitted in the form of packets of energy, which is basically known as photons, and each packet is having an energy of h nu, where h is the Planck's constant, which is having a value of 6.626 into 10 raised to minus 34 joule second, and nu is the frequency of the radiation. So we need to find E here in the question. Both H is given, nu is also given. So E is 6.626 into 10 raised to minus 34 into frequency of radiation is given as 5 into 10 raised to 14 hertz. The answer will be 6.626 into 10 raised to minus 34 into 5 into 10 raised to 14. The answer is 3.313 into 10 raised to minus 19 joule. In the question, as we can see, the options are given in terms of electron volt. So what is the relationship between electron volt is also a unit of energy, which is equal to the energy gained or lost by a single electron when it moves through an electric potential difference of 1 volt. The electron volt is also a unit of energy. So what is the relationship between electron volt and joule? 1 electron volt is basically 1.6 into 10 raised to minus 19 joules. So here, let it be X electron volt. We need to find X will be 3.313 into 10 raised to minus 19 joules, which will basically give you X is equal to 3.313 into 10 raised to minus 19 divided by 1.6 into 10 raised to minus 9, which will be this and this will go 3.313 divided by 1.6 is 2. So 2 electron volt is the answer. Here 2 electron volt will be the no. Majority of the upward going infrared radiation flux is emitted by the top of the troposphere. So this is the question. It is either true or false. So as we discussed, so let's see how the terrestrial radiation that is being emitted from the surface of the Earth is getting transmitted through the atmosphere. So we learned how the solar radiation is getting transmitted through the atmosphere and how we are losing the energy as it is passing through. Now let's see. Before answering this question, we will just see how the terrestrial radiation is being transmitted through the atmosphere. Transfer of terrestrial infrared radiation through the atmosphere. So consider the case of an infrared radiation at a given frequency nu that is emitted upwards from the surface of the Earth. So let this be the surface of the Earth. We have the this a small thickness dz. This is the total height z. So an electromagnetic radiation of frequency I nu s is being emitted from the surface of the Earth. This is what is being emitted from the top of the atmosphere. So I nu is what is being emitted from the surface, and I nu infinity is what is being emitted from the surface of the top of the atmosphere. So if this is the normal, the radiation is making an angle theta with respect to the normal. So the radiation is emitted at an angle theta with respect to the ground normal. So as the radiation travels upwards, it will be absorbed by the atmospheric gases. So I nu S is being emitted from the Earth's surface. As it is traveling through the atmosphere, the gas molecules will absorb this radiation. But this time, the emission of, and once these molecules absorb the radiation, it will start, after absorbing, it will re-emit the radiation as well. So this time, the emission of radiation by the gas themselves will contribute to I nu. So whatever is being absorbed is not lost. It will again be re-emitted by the gas molecules. So we don't usually lose the energy as in case of the incoming solar radiation. So in that case, whatever is being absorbed is actually lost. It is not reaching the surface, and that is like lost radiation. But in this case, water energy is actually being absorbed by the gas molecules. After the absorption, they will start re-emitting radiation as well. So this time, the emission of radiation by the gas molecules will contribute to I nu, since the atmospheric gases also emit radiation in the infrared range. So increase in the spectrum. So as we go up, actually there is an increase in the spectral intensity instead of a decrease that we saw in case of the solar radiation. So here, as the terrestrial radiation that is being emitted from the surface reaches the top of the atmosphere, there is an increase in the spectral intensity of the radiation. So this increase is basically given by the amount of energy that is being emitted upward by the gas minus the amount of energy that is being absorbed by the gas layer. So there will be some amount of energy that is being absorbed by the gas molecules, and there will be a certain amount of energy that is being re-emitted by the gas molecules. The difference between absorption and the re-emission gives you the amount of the spectral or the increase in the spectral intensity of the radiation as it is passing through. So let us assume that at an altitude Z, the radiation passes through a gas layer of thickness dZ, and the slanted path of the radiation through the gas layer is given by ds. So similar to before, so this is the thickness of the atmospheric layer, and this is the along the radiation path the thickness. So as before, dZ is basically given by ds cos theta. So let DAV be the differential amount of radiation intensity absorbed by the gas layer. DAV be the absorption, the differential amount of radiation that is being absorbed by the gas layer. According to the Lambert-Boger-Beer law, we know that the amount of radiation that is being absorbed by the gas layer is directly proportional to, or if we give the proportionality constant K nu I, is directly proportional to the mass density of the medium, the intensity of the radiation that is incident on the particular layer, and the distance of the along the radiation path, what is the distance that the radiation traverses. So dA nu is given by K nu absorption rho I nu into ds. Now let dE nu, so this is the absorption. Now after absorbing this amount of radiation, the gas molecules also re-emit the radiation. So let dE nu is a differential amount of radiation that is being emitted by the gas molecule. This is the emission. So dA nu is the absorption and dE nu is the emission. And let Tz be the after absorbing this much energy. Let Tz be the temperature that the gas layer attained. So Tsz is the temperature of the gas layer, and dE nu is the emission. So the emission, if E nu is the spectral emissivity of the medium, then the upward emitted radiation is given by TE nu is equal to the emissivity, which is epsilon nu, into this is the emitted radiation, which is a function of the temperature of the medium. So emissivity into the density of radiation into ds, B nu of T. So this is basically the B nu, which is the spectral intensity of the emission radiation from a black body of temperature T. So B nu of T is basically given by, this is the Planck's law, B nu of T is 2h nu cube by C square into 1 by a raised to h nu by kBt minus 1, where h is Planck's constant, nu is the frequency, c is the speed of light, kb is the Boltzmann constant, and T is the temperature of the black body that we are considering. So the net increase, and so this is the absorptivity. So we know what is absorptivity and we know what is emissivity. Absorptivity is given by K nu I absorptivity into rho I nu into ds, which is basically given by the Lambert Boga-Biot, and we have the emissivity, which is basically given by the emissivity, which is given by d E nu is equal to epsilon nu, which is the emissivity, into B nu of Tz into ds, where B nu is basically given by the Planck's law. The net increase in, so as we said earlier, the net, here we have an increase in the spectral intensity as the radiation passes through the atmosphere. Net increase in spectral radiation intensity as the beam passes through the atmosphere. As the beam passes through the gas layer is given by di nu is equal to emissivity minus absorption. How much is being absorbed minus how much is being emitted. So this is the increase in the net increase in the spectral radiation intensity as the beam passes through. And according to Kirchhoff's law, the fraction of radiation absorbed by a gas will be equal to the fraction of the total black body radiation emitted by the gas, which means the absorptivity will be equal to the emissivity, which means the K nu absorption I into rho I will be equal to K nu absorption I will be equal to the emissivity E nu. So from this we can write, so both d epsilon nu and this one, E epsilon nu and K nu absorption rho I will be equal. These two will be equal. So we can write the increase in the spectral intensity di nu. We can take that K nu absorption I into rho I into emissivity is B nu minus I nu of Z into ds. This is a function of temperature. This is the length that it travels. Rho I, K nu absorption I Basically B nu T of mine into ds. Now, if we want in terms of dz, we can write k nu I into rho I into B nu of dz minus I nu of z into dz by cos theta. Or we can write di nu by dz is equal to k nu absorption I into rho I into B nu of T of Z, which gives the emission from that uh, particular layer. And I mu of Z is basically the amount of radiation that is incident on that particular layer. Now again, here if we introduce the, so we can introduce the optical depth, which is T tau nu is equal to rho I K nu absorptivity I into T Z. Then d I nu, we can write it as d tau nu into b nu of iz minus I nu of z divided by cos theta. So this is the equation for d I nu. So if you want to get I nu of z, you can integrate it, then you will get the equation for I nu of z. So the integration will be a bit complicated since it has two terms, which is v nu of I of z and I nu of z. It's not as simple as like what we did for in case of solar radiation. So basically, if you integrate it, you will get two terms. The first term, which represents a fraction of terrestrial radiation that reaches the height z after being absorbed by the intervening media between z is equal to 0 and z is equal to z. The second term basically represents the upward emission contribution from all the atmospheric layers between the surface and the altitude set, with each contribution being attenuated by the exponential factor due to absorption by the thickness between the emission layer and the final Z location. So it accounts for both the absorption that is taking place in each layers and also the emission that is happening with each layers. So here the question was, majority of the upward going infrared radiation flux is emitted by the top of the atmosphere. So as we reach the top of the atmosphere, the amount of radiation is actually getting attenuated and attenuated. So the maximum amount of upward going infrared radiative flux will be emitted by the top of the atmosphere because the radiation is actually getting attenuated and attenuated. So this is true. So this basically gives you how the so the x-axis, the first one shows the temperature, and the y-axis shows the height of the atmosphere, and F with upward arrow is upward going infrared radiation flux, and F with the downward arrow is the downward going. As this, we know that there is upward going infrared flux. As the surface is emitting a radiation, the atmosphere absorbs the radiation and it re-emits it. It re-emits in both the directions, both upward and downward radiation. So there is always upward going infrared flux as well as downward going infrared flux. So this basically shows you how the downward and upward going infrared flux is changing with respect to temperature as we go up in the atmosphere. So here the next question is 50% of the downward going infrared flux is emitted at around 5 kilometers from the surface layer, from the sea level, sorry. 50% of the downward going infrared flux is emitted at around 5 kilometers from the sea level. So here we can see the F with downward arrow of Z. So this basically talks about this particular curve. So as we can see, this is having a very steeper curve towards the sea level. And as we are going up, the curve is becoming less steeper and steeper. So almost 50% of the downward going infrared radiation is being emitted actually below 2 kilometers. And then the till 2 kilometer, there is this curve is very steeper, and as we go up, uh, s- that steepness is actually decreasing. So almost 50% of the infrared downward going infrared flux is actually emitted at around 2 kilometer from the sea level. So this statement is actually false. 50% emission is actually occurring at a distance of 2 kilometer from the sea level. And if you see from the figure, the net upward flux reaches to 95% of its total value at the surface. The upward flux is actually it is getting attenuated and almost it becomes 95% of its surface value as it reaches the top of the atmosphere. So the top of the atmosphere or the troposphere emits most of the outgoing long wave radiation. Around 50% of the outgoing long wave radiation is emitted at z is equal to 5 kilometers. So different from the downward going long wave radiation. This thing is having a less steeper curve. It is almost equal. So like below 5 kilometer, almost 50% is being emitted. So the temperature is around 255 Kelvin, which is the emission temperature of Earth. And the temperature corresponding to this is around 255 Kelvin. And 80% of the downward infrared radiation originates below 5 kilometers. Whereas in case of infrared radiation, near to the surface, it is having a very steeper curve. So almost 80% of the downward infrared radiation is originating below 5 kilometer, and 50% of the downward infrared radiation is emitted below 2 kilometer from the surface where the temperature is about 275 Kelvin. The downward emission originates in the lower troposphere. So the downward emitting infrared radiation is mainly originating in the lower troposphere because most of it is emitted by water vapor and most of the water vapor is concentrated in the lower troposphere. So in case of downward emitting um, infrared flux, most of it is actually being emitted from the lower troposphere itself. As we go up, it is kind of decreasing and decreasing. Whereas in case of the outgoing long wave radiation, most of it is actually being emitted from the top of the atmosphere. So this is false. Now, the radiation from atmospheric layers contribute both to short wave and long wave radiation flux. This you will be knowing that it is false. This is false because the atmospheric layers are transparent to the incoming solar radiation or to the shortwave radiation. Incoming solar radiation, which is generally in the shortwave range, whereas it only interacts with the outgoing long wave radiation, which is in the infrared range of the spectrum. So the atmospheric layers only contribute to the long wave radiation flux. It doesn't contribute to the shortwave radiation flux. So this is false. So I think this is the next week sets question. So this was mostly about how the so till now we were discussing how the how the solar radiation is reaching the surface, how the Earth is emitting its radiation, how the atmospheric layers are absorbing it, and how it is re-emitting it, etc. So the solar radiation, as we come to the surface, it is decreasing and decreasing, whereas the outgoing long wave radiation, it is kind of getting attenuated, and the re-emission from the atmospheric gases are actually contributing to the outgoing long wave radiation. So the maximum outgoing long wave radiation occurs at the top of the atmosphere. So we learned both how it is interacting and everything. Now, this is actually part of the week sets of your NPTEL class. So the question is, which of the following gases contribute significantly to shortwave heating in the stratosphere? So shortwave heating is basically solar heating. We have ozone, water vapor, nitrogen, carbon dioxide. So we know that water vapor, carbon dioxide, and nitrogen are transparent to the incoming solar radiation, whereas ozone is the only gas which absorbs the UV radiation, and which is the reason for the temperature profile of stratosphere, which is actually increasing with respect to height, different from the troposphere, where we have a decrease with respect to height. So the answer is ozone. Ozone is the gas that contributes significantly to the shortwave heating in the stratosphere. So this basically shows you how the heating and cooling rates of different gases So, mm, so yeah, so the atmosphere basically absorbs and emits radiation, and it also heats up and cools down. As a result, which this basically determines the rate of heating and rate of cooling basically determines the temperature profile of the atmosphere with respect to altitude. So the atmosphere generally absorbs the incoming solar radiation, so generally it leads to heating. Whereas when it comes to the outgoing long wave radiation, it both absorbs as well as emits. So while it is absorbing, it will lead to a heating of the atmosphere, and while it is re-emitting, it will lead to a cooling of the atmosphere. So based on the characteristic wavelength of different atmospheric gases and its concentration along the atmosphere, how it is distributed vertically in the atmosphere, this basically determines the heating and cooling rates of the atmosphere at different heights. So as we know, the ozone is abundant in the stratosphere, which is um, around 25 kilometer or 50 kilometer of height. And as it absorbs the incoming shot, even though the maximum ozone is found at a height of 25 kilometer, the incoming solar radiation peaks at the top of the troposphere, which is 50 kilometer. So that's why we are getting the maximum heating due to ozone at a height of around 50 kilometer. Whereas the other gases such as the carbon dioxide, oxygen, NO2, etc., are very less in the stratosphere. And as we can see, there is no much heating that is happening at that range. Whereas at the that is actually leading to a cooling since it is transparent to the incoming solar radiation, and as it is absorbing and re-emitting the outgoing long wave radiation, we are seeing a cooling for carbon dioxide and water vapor in the stratosphere actually. So the next question was the water vapor largely determines the lapse rate in the troposphere. Um, yeah. Uh, so yeah, as we know, like it. So the atmospheric profile or the variation of the temperature in the troposphere is basically determined by the greenhouse gases that are present. And carbon dioxide, as we learned earlier, is a heteroatomic molecule. And it determines it actually it interacts with the outgoing long wave radiation. It absorbs and re-emits the outgoing long wave radiation. So basically, it determines the lapse rate or the temperature profile of the troposphere. So that is true. So the water vapor largely determines the lapse rate in the troposphere. It is true. As we can see, the temperature profile of the heating is mostly due to. So we also learned that the water vapor is mostly concentrated in that bottom layer, and because of that, the downward emission is larger in the bottom of the troposphere. We learned just now. So water vapor, which is highly found in the lower layers of the troposphere, largely determines. So as we can see, it is the heating rate is mostly determined by water vapor and the. So if the solid black line as a heating profile, we can see that it is mostly following the heating profile of the water vapor itself. So it is the temperature profile is largely determined the amount of water vapor present in the troposphere. It is mostly leading to warming rather than cooling in the troposphere. That also we can see. So as the amount of water vapor is decreasing as we go up in the atmosphere, the absorption that is happening due to the water vapor is also decreasing. So that's why we are having a lapse rate, or it is kind of decreasing as we go up in the troposphere. So water vapor does largely determine. So water vapor determines the temperature profile in the um, troposphere. Now the next question is the shortwave radiation contributes to both to cooling and heating of the atmospheric layers. So I just now told that the atmosphere is mostly transparent to the incoming solar radiation. and the solar radiation passes through the atmosphere without interacting with the atmospheric gases. So it doesn't contribute to even it doesn't contribute to both cooling and heating of the atmospheric layers. It is false. No. The shortwave heating rate reaches a peak at an optical depth of 1. So this basically gives you a graph between the solid line here. Yeah. The solid line gives you the heating rate. The dashed line the upward irradiance, negative of the upward irradiance. And the dotted line is the partial density. So partial density is basically how the amount of gas molecules in the atmosphere is actually changing. We know that it is basically changing as a function of rho is equal to rho zero exponential of minus z by h. So just with respect to height or z by h, how the partial density is changing from rho zero. That's what it basically gives you, the dotted line. So it is exponentially decreasing as we already know. And optical depth is how much is, it is a function of how much energy is actually lost as the solar radiation is, or it is basically a characteristic of the layer that we are considering, and it gives you how much energy will be lost as it is passing through a particular medium. So the optical depth determine the laws of the radiation. To put it simply, we know that I is basically given by I zero into exponential of minus 2. I zero is the amount of incident radiation. I is the radiation that is reaching the surface. It is basically exponential of minus 2. And we know tau is also varying with respect to height and with respect to the species that we are encountering. So we know that tau is basically given by K mu absorption of I into rho I, where rho I is the partial density and K nu absorption is the and K nu absorption is the species that it is basically encountering. So tau is also varying with respect to height. So I think I lost the connection. Just a second.